an awful lot about sensation, and now we are going to move into the concept of perception. So we now know how outside stimuli activates certain parts of our brain. Now we're going to talk about what our brain does with that. And so perception is excuse me, perception is the way that we organize and process all that information, and it's how your brain makes that movie that you watch, or it experiences that smell that you smell, or what have you. Um, Perception is the hard work of your brain that really gives meaning to your experiences. So, um, when you look at the picture on the right, what you see is two colored lines interrupted by a thick black line. But in reality, if you look at the picture on the left, those lines aren't connected. But your brain just naturally connects them in the picture on the right, and that's perception. That's not what you're seeing in terms of sensation. It's what you're perceiving in terms of perception, and that's what we're going to talk about, how you and why your brain does all those things. And when you look at this picture over here, there's something like 15 faces or something like that. You can pause it and try to find all of them if you want to, but um, what we have in front of us is just a picture of rocks and trees and what have you. But when you look at this picture, it doesn't take very long for all of these faces to start popping out at you. And that's because we perceive our world in one of two different ways. We have bottom up processing, and we have top down processing. And bottom up is when you look at the individual lines and colors and angles and shapes, and from that basic information you draw conclusions about the image. That's bottom up, where you start with the raw materials and then you work up towards a concept. Top down processing is what most of us do most of the time, where we start with concepts, schemas, ways that we see the world, ways of understanding the world. And then we, from those broad concepts, we then see individual specific lines, shapes, colors. Okay. So if you look at this picture and the first thing that you see are the faces, and then you see the trees and the rocks, that's top down. If when you look at this picture, you first see lines and colors and shapes, and from that you draw rocks and trees, and then you see faces, that's bottom up. Now, top-down processing is a really great way for us to simplify and understand our world. So if you look at this first sentence with the spaces, it shouldn't take you very long before you can come up with what it's saying. And that's because our brains just naturally create these schemata, which are just ways of simplifying our world. And it's like shortcuts to understanding what's going on around us. And so we create these are mental representations that we refer to as schemata. And these schemata then create these perceptual sets, which is just our predisposition towards understanding things a certain way. So when you look at clouds, you see shapes. When you look at any sort of pattern on a wall, maybe we tend to see faces that come out of it. That's because we have perceptual sets where we're looking for certain things. We're looking for faces. We're looking for recognizable shapes. And all of that is the result of this natural predisposition that our brains have towards top-down processing. The opposite then is bottom-up processing, where you see the individual data, you see, instead of seeing the letter A, you see 3 separate lines. Okay. And then we already did this in class, I think, where I told you to look at a piece of paper and try not to read the words. Reading the words before you even recognize the lines that make up the sentences or the letters, that's so reading the words first is top-down processing. Seeing the individual letters that make up, or sorry, the individual lines that make up the letters that make up the words that make up the sentences, that would be bottom up. So starting with the very basic constituents and then seeing the broader organization is bottom up processing. So this top down processing allows us then to see all kinds of illusions and tricks of the mind. Because we have these perceptual sets where we have expectations of things, we organize things naturally, it then causes us to see things that maybe aren't there or see things in different ways. So if you stare at either the letter A or the letter B, what you find is the circles that you're not looking at begin to spin. And this is an illusion. Obviously, it's not happening, right? There is no movement on this slide, but it appears to you that way. The same is true of this room. If you stare at any spot on the screen, the room begins to rotate. And that's because of our brains, the way our brain functions, we can take advantage of our processing and we can create illusions. We'll talk about how they work more in a minute. Before we get there, in order to simplify our world, we have all of these tricks of perception where we will naturally see things based on these rules that we have rather than what we're actually seeing. And one of those is perceptual consistency. So if someone is farther away, or if an object is farther away, we see it as smaller. And in each of these pictures, what we have is, so on the left, we have 2 images, and we've just moved the person in the background up and kept him the exact same size. And so in the picture on the left, he looks like he's normal size and far away. And in the picture on the right, he obviously looks really, really small. That's because our brain naturally recognizes things that are farther away as being smaller. The picture on the right, you got the 2 gorilla-looking animals. They're the exact same size, but because of the way the room is shaped, the one in back or the one above looks significantly larger. And so, yeah, so we got 3 examples of perceptual consistency. One is size that we just talked about. Another is color. So we understand light. Sorry, let me start over. So when a color is in the shade, we recognize it as darker, and we're able to understand shape based on shading. And then as objects move into the distance, they ought to be pushed back in the angles of our vision. And so we understand depth based on those angles as well. We'll talk more about these. These are all concepts that we're going to hit more. So another example of illusion is this Hermann grid. If you stare at the center of the grid, you're going to start to see these black dots that show up. And then if you scan across the grid, you'll see that there are no black dots. There just appears to be. And that's because our rods and cones work differently. Our cones have individual neural lines to our brain. Our rods, however, have to share neural passages or pathways. So it's almost like our rods have to hop on this neural bus. And so they don't have individual messages, they get grouped together. And because they get grouped together, we end up getting these blind spots. And the Hermann grid highlights that weakness. There's all of these rules about how we simplify our perception based on what we end up calling the Gestalt theory. And so, Gestalt theory basically says in order to understand our world, we follow all of these top down processing rules that make our lives a lot more simple. And these rules are pre wired to simplify how we understand our world. When we look at a square, we don't see four individual lines, we see a square because squares are easier for our brain to make sense of. So here's some of the way Gestalt psychology works. We divide our world into, or our visual world into two groups, the figure and the ground. The figure is what stands out to us when we're looking at, when we're talking to a friend, that person stands out in our visual awareness. So they're the figure. Everything behind that person falls back into ground. When you look at this image, you can see the columns are the figure, the black space is the ground. But then if you stare at the black space, all of a sudden it comes forward and you see these human shapes and they emerge as the figure, and the columns draw back into the ground. Next, closure. Our brains just naturally close images. Close images into organized objects that we can more easily understand. So for example, on the left you see a triangle, on the right you see a square, but the fact is there are no triangles and no squares in either image, but our brain just sees them. Next, we already mentioned perceptual sets, and our perceptual sets just give us a way of understanding our world. So look at these two lines. So read this set of words and then tell me what you think the last word is. And then read this line and tell me what the last word is. My guess is you picked different words because the first set of words puts your mind into the perceptual set of animals, and the second set of words puts your perceptual set into names. All right. Next, law of similarity says that we put similar objects together in our mind. When you look at this grouping of letters, do you see columns or rows? My guess is you see columns because your brain is going to put the X's together, the O's together, and that's simply how we see it. Law of proximity says that we tend to put objects together that are close to each other. So when you look at this list of letters, again, you probably don't see 5 separate X's and 5 separate O's. You probably see 5 pairs of X's and O's. Law of common fate refers to motion, and it says that things that are all kind of moving in the same direction, our brain puts together. So when we see a school of fish, we don't see 100 individual fish. We see one school of fish. All right, law of Prägnanz basically says that we have all of these different organizing principles, all these Gestalt principles in our brain, and our brain is usually lazy, so it's going to pick the simplest way of organizing first. So if you look at this box and read what it says, most of you probably didn't recognize the mistake. And some of you are still staring at it saying there isn't a mistake. And you don't see that there's two words repeated. Probably you see it now, but if not, the word "the" is repeated twice. Now, our ability to see in 3 dimensions is really, really sophisticated, amazing processing that's going on at an alarmingly fast speed. If we didn't see the world in 3 dimensions, we wouldn't be able to navigate it. We'd be falling over things, we'd be reaching out for things that were 100 yards away. Life wouldn't work. And so our ability to see depth makes living in the universe in which we occupy possible. Now, I know it feels simple, but you have to understand that the image that gets thrown up on the back of your retina is a two-dimensional image, and the information that goes to your brain is of two-dimensionality. Your brain adds depth as a distinct process independent of what you're actually seeing. So how does that work? Well, it turns out that we learn to see in 3 dimensions really young. So there was these researchers, and they were curious if babies were able to see in 3 dimensions, and so they built this complicated table that looked with plexiglass, where it looked like a baby could just step off the edge of a cliff if it wanted to. Now there was plexiglass, so it wouldn't actually fall. But what we find is that babies, as soon as they're able to climb, or as soon as they're able to crawl, have gained the ability to see in 3 dimensions, which means our ability to see depth is developed really early on, not at birth, but very shortly thereafter. And so how do we do that? Well, we do it in one of two ways. There's two kinds of cues that we use. Binocular cues, which are ways our brain can make sense of depth because we have two eyes on the front of our face, and monocular cues, which are cues that our brain uses based on the information, even if there was just one eye. So a cyclops would be able to see 3-dimensionally, not nearly as well as we can, but would be able to use binocular cues to make sense of its world. So binocular cues, basically, because we see the world through two eyes, we're getting two different angles on the things that we're looking at. Our left eye is seeing it from its angle, and our right eye is seeing it from its right angle, and they're not the same. What we're seeing is different from both eyes, and so the brain is taking left eye information and right eye information and going, oh, I know how far away this is because of the angle of our vision. The closer something is to our face, the more disparity there is between the two images. So if you put your finger right in front of your face, your left eye is seeing one side of your finger and your right eye is seeing the other side of your finger, and your brain has a really good idea of how far away that finger is because of how different the images are. When you're looking at something a mile away, you have almost no retinal disparity, and so you're really not able to tell distance based on those very, 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 very small differences. Accommodation works for things that aren't very far away also, and basically your eye has to focus on, if you're looking at look at something on your desk and then look at the floor, your eye is going to change its focus, and the way it changes its focus is by tensing the muscles around your lens. And so your brain recognizes the change in focus, and it can judge depth that way as well, as long as you're not more than 10 feet away from what you're looking at. All right. Convergence is this idea that as the closer something gets, the more our eyes have to move together, almost cross-eyedly, to follow it. So if someone's walking directly towards you, the closer they get, the more your eyes have to come together to focus on them. And your brain recognizes that convergence of your pupils and can use that to determine depth as well. Right. If you're a cyclops, you can't use binocular cues because you only have one eye. But there's other things that we can do. So we recognize depth of things based on a number of different tricks. One is interposition. So if something is blocking our view of something else, we just assume that that thing is closer. Another example is relative size. So if we know that two things are the same size in real life, but when we're looking at them, one is really small, we just assume that thing must be really far away. Relative clarity says the closer something is to our eyes, the more clearly we can see it. So if something is really hazy, it's probably far away. Texture gradient, relative height, relative motion, linear perspective. These are other monocular clues. I'll just go over them really quickly. So texture gradient, the more coarse something looks, the closer you are to it. So, wood, for example, from a long distance might look really smooth. And then when you get close and you look at it, you're like, oh, actually, this is pretty rough. It hasn't been sanded down. Relative height. Things look basically, the farther you're looking, the higher an object gets in your field of vision because it's moving farther and farther towards the horizon, right? So if the horizon is in the middle of your field of view, the farther something gets away from you, the closer to that horizon it is. So the higher in your field of vision, it's going to rise. Relative motion. You see an airplane fly past you, say 10 feet away from you, it is going to be moving. But if you see an airplane flying up above you at 30,000 feet, it's going to be moving relatively slowly. So slow movement means greater distance. And then, we all know that, you've got, when you're like in art class and you're drawing like a landscape or something, you have to pick that point on the horizon that all lines kind of converge on. That's your linear perspective. Lines draw in on this point on the horizon, and we use those converging parallel lines to determine depth as well. Oh, and then light and shadow. The farther something is, the dimmer that object is going to appear to be. All right. We also use context to determine our expectations on what's going to come next. And we've all been able to do that, right? You're talking with someone, and you guys do that with me all the time. I get stuck on a word, and then 3 students say the word that I'm trying to think of. You're using the context of the sentences that I've just spoken to guess what I'm saying next. And usually we're pretty good at that. Oops. Great. That's it already. So those are the ideas that you need to know about perception. That will get you through. Add that to what we've already discussed with sensation, and you are ready for our test next week. Good luck.